This is the video for Unit 8, Lesson 1, Solving Systems of Linear Equations by Graphing, and we're also going to look at nonlinear equations as well. So our goal is going to be solving a system of equations, and specifically we're going to focus on how to solve with graphing. So a system is a topic that you learned back in Math 1, and it's basically two or more equations that share the common variable. So we're looking for what is an x value and a y value that satisfy both equations, and that would be considered our solution. So if you remember, for linear systems, we have three possible scenarios. You can have where it's one solution. So for example, in this graph, we have one line that is y equals x minus 1. We have one equation that is negative 2/3 x plus 4. If I graph these two, they have an intersection at 3, 2. And that would actually be the solution to my system. So that means that when x is 3, y is 2, that would actually satisfy both of those equations at the same time. Another option we could have is what's called a dependent system. So that's if we graph it, we get the same equation twice. So for example, if I had y equals, this is the graph of y equals 3/4 x minus 3. And let's say I had two of the same exact equation. Maybe one was, they were written different, I just wrote them the same. They would share an infinite number of points in common. So there's infinitely many solutions. Sometimes we abbreviate this by calling it IMS, so infinitely many solutions. So we can end up with a system that has multiple answers that work. In graphing, they would look like the same line. The last scenario we can have is what's called an inconsistent solution, or no solution. So again, if intersections are solutions, parallel lines, and that's what these are, parallel, have no solution. So for example, this would be the equation y equals x plus 4, y equals x minus 5. These actually are parallel, they have the same slope. And so this would be a no solution because there's no intersection. So if we want to go ahead and graph these, it's really just that. We're going to look at where the intersection is, and that's going to be our solution to our system of equations. If we want to track them algebraically by substituting them in, we can. But again, we're just mostly just looking for our intersections. So for our first one, we're going to go ahead and graph this. This is a good review of Math 1. We're graphing in slope-intercept form. So our first one has a slope of -1. Our b is -2. We're going to go ahead and plot our y-intercept at -2 and go down 1 over 1. With graphing, if we're graphing by hand, it's sometimes good to do lots of points so we can see that intersection a little more clearly. And then this one, I have a slope of 2/3, a b value of 3. And so I'm starting at 3, and then I'm going up 2 over 3. I could also go down 2 and to the left 3. That's the same thing. And I can see I have my intersection, and that's actually my solution, -3, 1. So what that means is I would have to write my solution. That's my solution, is the intersection. If I wanted to check my answer, I can substitute this in, and I see 1 equals opposite of -3 minus 2. I would see then 1 equals 2/3 of -3 plus 3, and it actually is both check out. So that's how I know that's a solution to the system. For question number 2, it's pretty much the same thing. This one just happens to not be in slope-intercept form. This one's in standard form. You can graph with intercepts. I'm going to graph with slope-intercept form because we're going to find that sometimes it's harder to see the intersection when the points are not close to each other, if I'm drawing a line with 2 points. But again, you can graph with intercepts if you like, which you also learned back in Math 1. I'm going to solve for y just to get it in slope-intercept form. But again, lots of ways to do the same problem. So I'm going to graph here 2x plus 3. That's my first equation. And then I'm going to rewrite my second one. I'm going to add 4x. I see I don't have like terms, so I'm rewriting it. And then I'm going to divide everything by 2. So it actually works out that I have the same equation repeated, right? So I would start at 3 as my b, my slope is 2, and then I get the same equation twice. So I don't really have to graph it twice, I know it's the same, but what our solution would then be, it's infinitely many solutions. I'm going to write IMS, which means infinitely many solutions. So lots of answers would work. The you tries we're going to have you obviously try out. And then a topic that's a little new, but not necessarily, same concept, is, and you might see something like this on an SAT, is what happens when we have linear and quadratic systems. So basically we have a system of equations is considered a nonlinear system when it contains at least one nonlinear equation, and specifically a quadratic with an x squared. So the concept is the same. So intersections will be the solution. In this one, like this first system, I see I have a quadratic, I have a linear, and so where do these cross each other? They actually have 2 solutions. It crosses at -3, -2, and it crosses at -1, 0. So I actually have 2 solutions for this system, right? Because there's 2 intersection points. Another situation you could have with a linear and a quadratic is that it's a no solution, right? So you could see this green line, this linear does not cross this quadratic. This would be an example of no solution. And then finally, our last scenario we can have is if I have a linear and a quadratic, and let's say the vertex touches, or just one point touches, and that's it. So this one I had only one solution, right? So I could have one solution, I could have 2 solutions, I could have no solutions. So this one actually would have a solution at -2, 1, and then that would be my answer. If you have any questions, you can ask during class, sign up for T-Bolt time, or go to the center.